So, okay, hello everyone. My name is Pierre, and I'm going to present you the work I did during the beginning of my PhD with my two supervisors, which is Simon de Givry and Georges Katsirelos, on multiple choice knapsack constraints in graphical models. So first, I'm going to introduce you the weighted constraint satisfaction problem, which is an optimization problem that we typically resolve using a bunch-on-bound algorithm. And to get good bounds at each node of the search tree, the algorithms depends mainly on the structure of this WCSP. So we are going to see how can we derive good bounds if we have pseudo-Boolean constraints inside the WCSP. So I'm going to show you some experimental results where we can solve WCSP instances with pseudo-Boolean constraint inside and conclude over this work. So to introduce this WCSP, I will begin with the constraint satisfaction problem that I think many of you already know. So in this problem, we have a set of discrete domain variables. I have a set of constraints, and I want to find an assignment that satisfies all the constraints. Okay, and here we are talking about the weighted versions of these problems, which means that we don't have a binary violations of the constraints, but we have different violations of the different degrees of violations of the constraints, which can apply different cost penalties. So here I represented two constraints. So as a table, so as you can see in a CSP, either a tuple is forbidden or it is allowed, while in the WCSP, when we have an assignment, it has attributed a cost, and this cost can be between 0 or plus infinite. And of course, the lower is the cost, and the better it is. And we use a plus infinite cost to represent a forbidden tuple. So this constraint, we represent them as cost functions. That's why to define a WCSP problem, we use cost functions networks. So to define a cost function networks, we have a set of discrete domain variables. Once again, we have a set of scopes, and for each scope, we associate cost functions that will associate for each tuple inside the scope a positive integer cost that can be plus infinite. As I said before, the infinity cost corresponds to a forbidden tuple, forbidden assignment. And so we have a set of cost functions, and the WCSP, the weighted constraint satisfaction problem, is to minimize the sum of all these cost functions. So of course, this problem is an NPR problem, as it is a generalization of CSP. As you can see, if all the cost functions only attribute 0 and plus infinite cost, then it's just like hard constraints defined in the CSP problem. So a very small example to show you how it looks like the WCSP. Here I have a weighted constraint satisfaction problems with only 2 variables, and I have 3 cost functions. So I have 2 cost functions that has unary, we call unary cost functions because they only have 1 variable inside the scope. So it is a 2 at the bottom. And I have a binary cost function that links 2 variables. And the objective is to find an assignment that minimizes the sum of all these cost functions. So you can see this problem as trying to minimize some big objective functions that is split into small cost functions. So to solve these problems, we get lower bound, as I said, and to get this lower bound, we use the concept of equivalence preserving transformations. So we said that 2 WCSP are equivalent if for any assignment, they have the exact same cost inside the 2 WCSP. It means that any assignment has the exact same global cost in the 2 WCSP, but if you look at the local level, the cost functions may have different costs. And so we can get we can take one WCSP and get an equivalent WCSP by doing what we call equivalence preserving transformations, so EPT, that we will use many times during the presentation, which is basically a move of cost from one cost function to another cost function. And we will use this to get lower bounds. So why does it help us to transform a problem into an equivalent problem? I will show you again with this small example. So we want to get a lower bound of this very small problem. And so simple things we can do is to try to apply some property on our cost functions. So a simple property would be to look at all the cost functions, and we need to verify that every values can be assigned to some tuple that will have a zero cost. And if we look at the binary cost functions here, we can see that the assignment x equal a is only associated to positive cost. So we have AA equals to 3 and AB equals to 2. So what we can do is to transfer this cost to the unary cost functions. So how can we do that? We simply decrease the cost of all the tuples that use x equal a inside the binary cost functions. And to balance this, we increase the unary cost of the value x equal a. And so I obtain a new WCSP. So the two WCSP are equivalent. Every global assignment has the exact same cost, but as you can see, locally, my cost functions has been modified. And now I can observe in my unary cost functions of x, the two values of x as a strictly positive cost. So once again, I can transfer this cost to a particular cost functions, which is f0 or f empty set. So this cost functions is very particular and its scope is empty, which means that it will be used in any assignment. And if we don't have any negative costs inside our cost functions, which is a property that we will keep during a search, then this f0 is a natural lower bound of our problems. So we will use this f0 to inside the branch-bound procedure where we are going to try to maximize it at every node of the search tree. So objective now is to find a sequence of EPTs that maximize this f0. So a sequence of EPTs that will maximize this lower bound. But if we consider only integer cost, finding such sequence of EPTs is an MPR problem. So what research has been focused on is to apply what we call the soft local consistency algorithm. So as I said before, it's kind of applying local property on a subset of cost functions, and then we can increase the lower bound thanks to that. So what they do is that they look at a subset of local cost functions, they prune the inconsistent values, and they compute a local minimum. Then they use a sequence of EPTs to increase f0 by this local minimum. And they do that for every local cost function. So there is plenty of different level of local consistency. I won't give too much details on them here, but what you need to know is that for them to be efficient, we need a full table representations of all the cost functions. So we need to explicitly give the cost associated to each tuple inside a scope, which is, of course, impossible for global constraints because they can have an exponentially large number of tuples. So global constraints are usual in the CSP. So we have all diff, among, and so on. And they can have an arbitrary number of variables inside the scope. So how can we have, how does this global constraints appears in the WCSP? We can, for example, have hard global constraints. So just like in CSP, so an assignment either verifies this global constraint and it has associated to a zero cost, or it doesn't satisfy this constraint, and then it has an infinite cost. So if we have a hard global constraint, then what we can do is to delete the inconsistent values. So it will be just to apply a propagator, just like in CSP. But if we do that, we don't gain any information to compute a new lower bound. So what we are doing here is that we are going to consider one hard constraint plus the unary cost. So hard constraint plus cost. It is something that has already been done with other global constraints. Another way that can appear the global constraints in WCSP is soft global constraints. So I won't give too much detail here on them, but basically it's a global constraint. And if depending of how you violate the constraints, it will imply different cost penalty. So it's not anymore a hard global constraint, but I won't give too much details on that today. So here, the global constraint that will interest us is a pseudo-Boolean constraint. So it is written that way. So we have a pseudo-Boolean variable xi that is multiplied by a positive coefficient, and we want to have the sum of these that is greater than a positive coefficient. And so what we want to do with this pseudo-Boolean constraints, we want to be able to solve a WCSP with pseudo-Boolean constraints inside. So more precisely, what we want to do is we want to find a local lower bound looking at one pseudo-Boolean constraint plus the unary cost. we find the local minimum of this problem. And then we want to define the sequence of EPTs to increase F0 by this local minimum. And of course, we want to do all of that without having a full representations of the pseudo-Boolean constraints, because once again, it will imply maybe an exponential number of tuples. So one example to show you what we really want to do. So here I have a small problem with only 3 variables. I have the 3 unary costs that corresponds to the variable, so it's the bottom. And I have one pseudo-Boolean constraint at the top. So it's a pseudo-Boolean constraint because, as you can see, we associate for every values of inside the scope. So every values of every variables positive some weights. And so here we have x small a takes value 1 if x equals a inside the primal problem. So that's why we have pseudo-Boolean variable. And I represented the full table of the pseudo-Boolean constraints, which is something we usually want to avoid. So what we want to do with this problem is we want to minimize the sum of all of this. So what does that mean? In the end, we want to minimize a linear function, so the sum of the unary costs, such that a pseudo-Boolean constraint is verified. So you may know this problem, it's a knapsack problem. And if we consider that every variable must be assigned to at most one value, we get the multiple choice knapsack problem. So we want to minimize the sum of the unary cost such that all pseudo-Boolean constraint is verified and that each variable is assigned to at most one value. So this problem is NPR to solve. And because we are running this inside the bunch and bound algorithms, we want to keep our algorithm in a polynomial time. So what we are going to do is that we are going to relax the integrity constraint, and we get the relaxed multiple choice knapsack constraints, which is here solvable in a polynomial time. So it means that we can get an optimal solution here, which is here where x equal b, y equal a, z equal a with a cost of 3. So here I'm lucky because the optimal solution of the relaxed problem is also the optimal solution of the integer problem. Okay, so once I found this optimal solution, I said I wanted to find the sequence of EPTs to increase F0. So the sequence, I will give it to you here. So for example, it would be to transfer a cost of 3 from x equal a to the pseudo-Boolean constraint. So it is what is written in blue. We want to do the same for y equal a. So it's what is written in red. And we can also take a cost from the pseudo-Boolean constraint and put it on z equal b. So this is the things in green. So it might be, so to find this sequence of EPTs, it turns out that looking at the reduced cost associated to each values give us the correct and the working sequence of EPTs, which means that we solve the relaxations of the multiple choice knapsack problem. Then we look at the reduced cost of each value. So we can get the reduced cost by looking at the dual optimal solutions of the multiple choice knapsack problem. And we get this sequence of EPTs. And as you can see, we can see that in the pseudo-Boolean constraints, all the tuples has indeed a cost that is greater than 3, which means that we can take a cost of 3 from the pseudo-Boolean constraints and put it in F0. So if we do this sequence of EPT, we indeed increase F0 by 3, and we don't induce any negative cost inside our cost functions. So this is what we wanted to do. But what we can still observe is that inside the table representations of the pseudo-Boolean constraints, there are still some costs remaining. And I need to have access to this cost. I can't just put it away and don't look at it anymore. So I need to have a way to know the cost associated to each tuple inside the pseudo-Boolean constraints. But as I said before, we don't want a full table representation. So how can we get access to this cost? We can do it using what we called delta's cost, which are quantities that will capture the cost transferred from the unary cost functions to the pseudo-Boolean constraints. So we have one delta cost per value, and we have one delta cost that represents the quantity of cost moved from the pseudo-Boolean constraints to F0. And once we update, so we have to update this delta cost every time we are doing an EPT between the pseudo-Boolean constraint and the unary cost. And once we have this cost, we can simply get the information inside the full tables by looking at this. So if the assignment that is given is verifying the pseudo-Boolean constraint, then we just look at the sum of the delta cost. And this corresponds to the cost that is remaining inside the table. And if the assignment doesn't verify the pseudo-Boolean constraint, then it has a cost of plus infinite. Okay, so so it means that this delta cost, we need to take into account when we solve the multiple choice knapsack constraint. So it means that now we slightly modify the objective functions and we want to minimize the sum of the unary cost plus the delta cost, which corresponds to solving exactly the problem we want, which means the unary cost plus the table representing the pseudo-Boolean constraint. So if we look again at our example, so this was the initial state. So we had in blue the unary cost. The delta cost initially are all 0. We find an optimal solution. We applied a sequence of EPTs and we update all delta cost. So now in red, as you can see, the delta cost has been modified and the unary cost as well. And so now if we solve these problems, we can find that the optimal solution is 0, which is what I wanted. And moreover, if I only look now at the delta cost, which means if I only look at the kind of the pseudo-Boolean constraints only, I can see that there are several optimal solutions. And indeed, I can find one optimal solution with a cost 0 for every values of every variable, which was a property that I wanted to verify before. I said that for every cost function and every values, I want to have one tuple that has a cost equal 0. So this gives us an hint that the sequence of EPTs that we applied was good and that it is a working algorithm. So the algorithms look like this. We solve the multiple choice knapsack problem, so the relaxed versions of this multiple choice knapsack problem. We define the sequence of EPT by looking at the reduced cost, and then we apply the sequence of EPTs, and we don't forget to update the delta cost. So we did, and we applied this procedure for every pseudo-Boolean constraints in my problem at every node of a search tree. So we implemented this work inside the WCSP solver toolbar 2, which is an open source solver that you can try if you want. So the first benchmark we tried was the knapsack problems with conflict graph. So in these problems, we have between 60 and 1,000 Boolean variables. We have one linear objective, so it corresponds to unary cost inside the WCSP. And we have one linear arc constraint that links all the variables. It means that we can have pseudo-Boolean constraints with at most 1,000 variables. And we also have a graph of incompatible pairs of values that corresponds to binary arc constraints in the WCSP. And so we tried all solvers against Cplex using different encoding, and we observed that toolbar 2 was competitive against him, against Cplex on several benchmarks, which means that toolbar 2 is indeed capable able to gain information from the linear constraints and to get a nice lower bound thanks to the algorithm we implemented. The second problem we looked at was the computational protein design problem. And so this is a problem where there is a quadratic objective function. So it corresponds to binary cost functions in the WCSP, and the difficulty of these problems comes from the very large domains. So to solve this problem, toolbar 2 is already is the state of the art, and we are looking at a slightly different problem because we want to produce a sequence of diverse solutions for this problem, which means I don't want to find only one optimal solution, but 10 solutions that are all different from one of the other. And to ensure that two solutions are different from the other, we use what we call Hamming distance constraints. So it means that we solve a first time the problem, we get an optimal solution. we add an Hamming distance constraint. We solve a second time the problems, but with this new constraints, we obtain a second solution. We add again an Hamming distance constraint, and so on. So at the end, we can get 9 Hamming distance constraints. So previously, toolbar2 used automata-based encoding, and now that we can use pseudo-Boolean encoding, we just directly encode the Hamming distance constraint into a pseudo-Boolean constraint, and we can observe that toolbar2 was quite more effective to solve this problem. So to conclude, this works allows the better modeling flexibility for the WCSP framework. It's now possible, for example, to take an arbitrary global constraints and to decompose it into linear constraints, and then encode and then put this into a WCSP framework and solve the problems, which was not possible before because we will need to define some way to propagate this global constraint. So now toolbar2 is able to solve more problems than before, but we have one main drawback, that is that we only look at the local lower bounds, which is sometimes ineffective compared on some instances where there is a large number of linear constraints and where ILP solver or pseudo-Boolean constraints, which get global bounds, get better results. And finally, this works open up the possibility to have a learning mechanism inside the WCSP framework, which is what the purpose of my PhD. So thank you for listening to me. I will be happy to answer. Yes?
Thank you for a very nice presentation. I just have a question about the title, because in the title there is graphical models. I don't see the connection.
Okay. So it's a CFN is a graphic, it's a type of graphical model. Okay. So the cost functions network that I introduced at the beginning, it's a type of graphical models. Yes.
So the multiple choice problem, I think there are very strong approximation algorithms. I think even an FP does, and I wonder if that can be helpful.
We didn't try FP class for the moment. Yes, maybe it could be useful. It's true that at the beginning of my PhD, I didn't have the knowledge I have now, and so I thought that we absolutely need a relaxed optimal solutions. But no, with the knowledge I have, it's true that probably that just taking using FP task algorithms to get an approximate solutions would be worse maybe. But we observe that it's not what's taking time during the procedure. Like finding the optimal solutions of the relaxed problem is not the difficult part of the problem.
It seems really quite on the same performance as CPAIOR. Do you know if you get the same lower bound for the global problem?
No, we don't have the same lower bound because we always look at the local level while they are looking at the global level.
Yes, so since you have iterations, maybe it's a little like pivoting, I would say.
Yeah, I don't know if you can really compare because even in the branch-on bound, we have two very different branch-on bounds. Yeah, I didn't compare on that level. I didn't. No. Yes.
So maybe you can start the search with your relaxation, and then when you go deep in the tree, the knapsack problem becomes simple, and then you can do an exact.
Yes, we tried to do that, but what we missed was when do we say that okay, now solve the integral versions of the knapsack problem. So it's finding the threshold to say okay, no, I don't solve anymore the relaxed versions, but the integral versions, and it's difficult to know when it is worth it to do it, because especially when you have a very large number of pseudo-Boolean constraints, solving at each step the ILP is very time consuming. Yes.
Have you had the chance to see when your approach doesn't improve on toolbar2?
When does it improve?
So you said that this is something that you can add to toolbar2 to improve performance on the protein. Something I don't remember the name of the benchmark.
Yes.
But to find out when it doesn't work, when it's not an advantage of using it.
No, not really, because okay. So this works. This allows to handle pseudo-Boolean constraints. So when there was no pseudo-Boolean constraints, or algorithm, just don't use it. And before, it was not possible to model linear constraints in a WCSP. So it means that before it wasn't possible to solve the problems with linear constraints. So that's the difference. And for the CPDs, the only difference is it was a typical constraints that was encoded using the pseudo-Boolean constraint or previous automata-based encoding. And I think there is only one instance where the automata-based encoding was better. Yes?
Can you use an MGD instead of a table constraint?
So I know that in toolbar 2, at least, we need the full table representations to make the algorithm work. So I don't know if it was a question, but yeah, I need the toolbar 2 needs to have the information that one tuple has this exact cost. So I don't know if I don't think we can apply MTD.
This is a limitation, the number of solutions. If you could have an MTD, you will result more.
With MDD, you can only subtract from the edge. There's less scope.
Yes.
I have just a question on the naming of your constraints. Is this like, I don't know, so in CP, this constraint is called Boolean constraint? Or like on the mid side, you could just say that it's maybe a complement Knapsack or something. Because for us, Boolean constraint can also have multiplications of binary variables.
Yes, yes, we just named it pseudo-Boolean constraints. Okay, I don't. So because it's pseudo-Boolean constraints inside the problem. Can you reformulate?
Yeah. So basically, so I'm just asking because I don't know. For me, a pseudo-Boolean constraint can be more than you have only a linear version of it. It's like greater equal definition basically. And I'm just asking if this is like, maybe it's a common theme, I don't know that. So I was just wondering about it. But for me, it's just a Knapsack.
The name comes from the SAT community, so we won't take any responsibility for that. Also, you can always map every pseudo-Boolean inequality at least to that form. So that's why they only consider that.
Yeah.
Yes. That's true. You can put inferior or equal constraints or even negative coefficients, and you can always get back to it.
Okay, since we are short on time, perhaps we should.
Yes,
Thank you very much.
Thanks for